So we're gonna focus now on a new premium principle. And that premium principle will look at the profit and loss at the level of a group of insurance contracts. So let's see how that works. And this is a new way of thinking. So let's see how that goes. So if you look at the actuarial equivalence principle, then that principle sort of imposed an equivalence between the EPV of the benefits and the EPV of the premiums. So there you see that there is not no explicit accounting for a loading for profit, right? So in traditional insurance, if you want to include a load for profit, so that means if you want to charge a premium that is a little bit higher than the technical premium, than the premium that you would construct by actuarial equivalence if you do not take a profit loading into account. So if you want to charge a premium that is a bit higher so that you take a loading for profit into account, then one thing that one could do, and that has been done in especially a traditional valuation framework, is to play a little bit with the assumptions that you make in terms of the basis that you use for valuation. And the basis that you use for valuation, that's about the interest rate that you're using, about the survival model that you're using. So you could say, for example, that you're going to use in your calculations a lower interest rate than actually expected. And then the impact will be that you charge a slightly higher premium, right? So you charge a higher premium to make some profit in this via this premium collection, right? So that's one way how you can play with the assumptions that you make in your valuation basis in order to take this load for profit into account. You could also play with the mortality assumptions, but then of course it depends on whether you're dealing with an insurance product or with an annuity product, and that will influence the way how you should change your mortality assumptions in order to take this loading for profit into account. And if you say with the insurance products, if you have higher mortality than expected, then it means that you expect to pay out more death benefits. So that will increase the premium. If you work in the other way with a life annuity product, if you assume, or if you use in your valuation basis a lower than expected mortality assumption, then again the premium will increase, because then you expect to pay out the life annuity benefits for a longer time, and that will have an increasing effect on the premium. So these were some traditional ways to step away slightly from this technical premium and to use an actuarial equivalence, but with a valuation basis that changed in order to come up with a higher profit, a profit that with a higher premium, a premium that would take some profit margin into account. And what we're now going to do is we're not going to use this kind of reasoning. So we're not going to play with the interest rate or the mortality assumptions, but we're going to look at the profit or the loss first at an individual contract and then at a group of contracts. And we're going to use the distribution of the profit or loss at the level of a group of contracts. We're going to use that distribution to determine a certain premium that will reflect or that will correspond to a certain level of profit or loss. And a first consideration to keep in mind there is that each individual insurance contract that you sell to a client will generate a profit or a loss. And what we mean with that is that you sell this contract, you receive a certain premium as an insurance company, and at the end of the contract, you also know what you actually paid to the policyholder in terms of the benefits, right? So for every contract, you can see what is the difference between the present value of the benefits that I paid, and what is the difference with the present values of the premiums that I collected, and was that a positive difference or a negative difference? Was there a profit or was there a loss, right? So the equivalence principle, the actuarial equivalence principle, works with the EPV of the benefits and the EPV of the premiums, right? So there we do not take the actual realizations in the contract into account. And that the technical premium determined by the actuarial equivalence principle matches the EPV of the benefits and the EPV of the premiums. If you look at a large group of IID contracts, then the actual profit from the group of contracts will be reliably close to the expected profit. And then you can use instruments like the central limit theorem to say something about the distribution of the actual group, of the actual profit in a group of contracts. And that's what we're going to do today. So let's see how that works. And we're going to start with an example of a very simple product so that we can get a bit of grip on this profit and loss on a single insurance contract. So here we consider a one-year term insurance with a sum insured of €1,000 that is payable at the end of the year of death. We're going to suppose that the life is subject to a mortality of rate of 0.01 over the year. The interest rate is 5%. There are no expenses. Yeah. So it is a very simple product because it's a one-year term product. Okay. The death benefit is payable at the end of the year of death. So we can easily calculate the technical premium on this product. It's a single premium P. The EPV of the premiums is just P. And the EPV of the death benefit in this one-year term insurance contract, that's 1,000 times V times QX. The interest rate was 5%, the QX was 1 over 100, so you can calculate the premium P in this particular setting. Yeah, so here, the EPV of my death benefit it's simple because I only have a one-year cover in this example. Now, if I look at the future loss random variable, and if I look at the actual outcomes or realizations that this loss random variable can take, well, I only have a one-year contract. So there are two scenarios that can unfold over time. So either my policyholder dies at age X before reaching age X plus 1. And in that case, my loss measured or expressed at time 0 would be the death benefit of 1,000 discounted to time 0. So that's 1,000 times V minus the premium P that I received as an insurance company at time 0. So if my policyholder dies in this one-year contract, then I'm actually facing a loss on the contract, and the present value of this loss is 942.86 euros. Why is that? Because I have to pay the death benefit and I only collected the premium equal to 9.5, right? So there is a loss on this contract, and this loss occurs with a probability of 1 over 100, because that's the probability that my policyholder will die in this first year. On the other hand, if my policyholder survives until age X plus 1, then I receive the premium, right? But as an insurance company, I did not have to pay the death benefit, right? So in that case, my loss is negative. So it's in fact a profit, and it is a profit equal to 9.52, which is the present value of the premium that I receive at time 0. So with 99% probability, I'm making a profit on this contract. So if I calculate my expected loss or my expected profit, then I get 0, right? I get 0 because I calculated my premium with actuarial equivalence. So I'm imposing that the premium should lead me to an expected loss equal to 0. But here you see it also in a different way. If you look at the actual realization of the loss in the contract, then you can here also, once again, in a different way, see that the expected loss on this contract is 0 if I charge a premium P equal to 9.52. Okay, so this is for a single contract. So the thing I want you to realize, because that's a reasoning that we haven't been using so far, is that here with this way of writing it, we're taking the perspective about, yeah, what is actually happening in this 1 year contract. Will my policyholder survive? What is the corresponding loss then? What is the probability of survival? And on the other hand, what if my policyholder dies? What will then be the loss on this contract? And what is the probability that this policyholder dies? Yeah. So here it's in fact a Bernoulli experiment, right? It is a 0-1 experiment. You survive or you die as the policyholder in this contract. And now we're going to step to a group of contracts. Yeah, and we're going to suppose, for example, that our insurance company issues 100 contracts of this particular policy. And we're going to assume that all the lives covered by these 100 contracts, that they can be assumed to be independent. Yeah? So if we then write down, or if we then say, what if all these lives survive for the year? Well, then there is a profit, of course, because then we never had to pay the death benefit of, what was it again, 100,000, no, 1,000 euro. So if all my lives survive for the next year, we've got profit. If one life dies, there is no profit and there is no loss. And if more than one life dies, there will be a loss in this portfolio of contracts. So how can you see that? Well, the first bullet is clear. Huh? If all the lives survive, you do not have to pay the 1,000 euro death benefit, so you definitely make a profit. If one life dies, you'll have to pay the 1,000 euro once. You can calculate the present value of this 1,000 euro. That was 952 something. And you know that you collected the premium equal to 9.52. You collected that one 100 times at time 0. So you see then in the second bullet that the income is in equilibrium with the outflow that you have to pay. But as soon as more than one life dies, there will be a loss in this portfolio, because then you have to pay the death benefit more than one time. Yeah? So with a large number of contracts, we will see later on that the actual loss on the portfolio can be, or more or less, is close to the expected loss on the portfolio. And that's the kind of reasoning we want to build up now in order to determine a certain premium level as a function of the amount of profit or the level of profit that we want to impose on this portfolio of contracts. Yeah? So that's what we're going to do when we're talking about the portfolio percentile premium. So this is a different way to determine premiums. It is no longer using the actuarial equivalence premium, and we're going to use the portfolio percentile premium. And we're going to assume a portfolio with identical and independent policies. And we're going to denote the loss on each of those policies with L0I, where the I runs from 1 up to capital N, and capital N is here the number of contracts that I'm going to sell in my portfolio. Yeah? So these future loss random variables, that's how we introduced them so far. But now we have one such variable for each contract that is sold to a policyholder. So if we look at the total loss in the portfolio, then we're dealing with the sum of those L0I's, right? Where the I runs from 1 up to capital N. And then we can say something about the expected value and about the variance of this random variable L. First of all, for the expected value, that is the expected value of the sum. That's the sum of the expected values. They all have the same distribution, so they have the same mean. So we get n times the expected value of one of these loss random variables. If we look at the variance, this is the variance of a sum, but the random variables are considered to be independent and have identical distribution. So you get n times the variance of one of these random variables L, right? So these are the expressions that we have. And now, of course, I guess you see the story coming. We can use the central limit theorem to say something about an approximating distribution for this random variable L, using its mean and using the expression for its variance. And we're going to determine a premium P such that with a certain probability alpha, we make a negative loss on this portfolio. And a negative loss means a profit. So what we're actually imposing is that with a certain probability, we want to make profit on this group of insurance contracts. And we want to determine the premium P such that with the given probability, we're going to achieve a profit. Okay, that's the condition that we're going to impose that will lead us to an expression for P, that will lead us to a way to calculate the P. Okay, so this is different from what we did in the actuarial equivalence scheme, because there we said at the level of an individual contract, we would balance the EPV of the benefits and the EPV of the premium. So there at the level of an individual contract, you would have a loss or a profit equal to 0. Okay. So what are we going to do? We're going to work with the distribution of L, and we're going to use the normal approximation for that, relying on the central limit theorem, right? So we're going to work with a normal approximation, and we're going to write down the probability that there is a profit. The probability that there is a negative loss can be written as follows, where we standardize the distribution of L. So we subtract the mean, we divide by the standard deviation. So we also have to do that at the right-hand side of my inequality. So I'm going to say, well, if you look at L minus the expected value of L divided by its standard deviation, I can approximate that with a normal distribution. So I'm left with evaluating the cumulative distribution function of a standard normal, the capital Phi. I want to evaluate that in this point, and I want to put this probability equal to alpha, right? And now you will say, yeah, where does the premium come in? Well, the premium kicks in because this expected value of L is going to be a function of the unknown premium. And also the standard deviation is going to be a function of the unknown premium P, right? So we have to solve the following equation. So we have to calculate which P leads us to the following expression for a given alpha. And that is what this portfolio percentile premium, what that will be about. So what we did is we looked at the expression for capital L, which is expressed as the total loss on a portfolio of contracts. And we impose this particular condition here. We want to have, with a certain given probability alpha, we want to make a profit, and we want to know which premium P will lead us to this profit with given probability. Yeah, that's the job, that's the kind of calculation we want to do in here. All right, so let's try this example. So we're here looking at whole life insurance contracts issued to lives age 30. The sum insured is 100,000. It's payable at the end of the month of death. We have level monthly premiums payable throughout the term of the policy. We've got initial expenses incurred at the issue of the policy, which are 15% of the total of the first year's premium. Renewal expenses are 4% of every premium, including those in the first year. We have a given survival model. We've got a given interest rate. And we want to determine the premium either by the equivalence principle or using this portfolio percentile principle. And think about Sally's question. Here we say that the probability that the future loss is negative should be 95%. And we can assume that there are 10,000 identical independent policies sold in our contract, for this particular product. Yeah. So we start with part A. That's something we learned already. So we're looking at whole life insurance policies payable at the end of the year, at the end of the month of death, sorry. 100,000 euro is the death benefit. We've got level monthly premiums payable throughout the term of the policy. And we've got a few things with these expenses. So we've got initial expenses, 15%, and we've got the renewals equal to 4%. Yeah. So I'm going to write down the actuarial equivalence. I'm going to start with the EPV of the premiums. So there we said they are payable monthly throughout the term of the contract. Well, it's a whole life insurance. So the term here is lifelong. And do remember, I'm using here the monthly life annuity. And I have to take into account then if P is the monthly premium, then 12 times P is what I would pay annually in this contract, right? So we learned how to do this. And we learned that this is the correct EPV then. That's what we studied in chapter 5. So P is the monthly premium. Where is this number coming from? Well, I could do the numerical evaluation. That's not the essential point of this exercise, but I've got a given interest rate. I've got a given survival table, so I could do the calculation of this EPV of the monthly life annuity. Then I'm going to look at the EPV of my benefits. I've got a whole life insurance. The insured amount is 100,000, which is payable at the end of the month of death. So I need to value this particular product here. Again, I could do the maths or I could do the numerical calculation and I get the number that you see over here. The last ingredient to take into account are the expenses. So we've got the EPV of the expenses. So do remember that was 15% of the premiums paid in the first year. So that's 15% of 12 times P. And then every year we've got a renewal expense of 4% of the premiums that you're paying, also in the first year, right? So that means I'm going to add in the expression for the expenses 4% of 12 times P multiplied with the EPV of a whole life annuity, right? For the first, for this first part, I'm not taking any survival probabilities into account here, because here I'm going to assume that I'm going to value this expense at initiation of the contract, so that's at time 0, and I'm just going to take their 15% of the premium that is paid in the first year as my initial expense to be taken into account at time 0. So how do I write down my actuarial equivalence? I've got the EPV of the benefits plus the EPV of the expenses, and I subtract, or I put that equal to the EPV of the premiums. I solve for the unknown P, and that gives me the so-called equivalence premium in this contract, right? Any questions on that? So this is what we learned in the past. Yeah, that's what we learned so far. And now we're going to do a different way of calculating the premium. So what we're now going to do is we're going to look at the loss at an individual contract. And we're going to write down the loss as a random variable. And if we look at the loss as a random variable, we've got the present value random variable that takes care of the whole life insurance part. It's the 100,000, which is payable at the end of the month of death. And then we know from chapter 4 that if you look at the present value random variable, you're going to work with this kind of expression because you're paying at the end of the month of death. Then you've got the initial expenses. That's the 15% of 12 times P. No stochasticity there. And then you've got the renewal expenses minus the present value random variable that takes care of the premiums, right? And here you recognize the random variable that is corresponding to the present value of a life annuity that pays monthly, right? That pays monthly at the beginning of each month. So why do I get this minus 0.96 times 12p? That's because I would have plus 4% of 12 times p minus 12 times p times the same expression over here. So if I take these two together, I'll get the minus 96%. Okay. What is the expected value of this thing? Expected value of this thing, I would calculate it as the expected value of this whole expression. And of course here, I recognize then, if I would take the expected value, I would recognize the EPV of the whole life insurance that pays at the end of the month. And here I would recognize the EPV of the whole life annuity that pays monthly, right? So if you want to make sense out of the numbers that you see over here, then you should go back to my previous screen. So then you should recognize this number, and you should recognize that I combine this one with the number that you see here at the bottom, right? So if I combine those in the correct way, then I would get the expression that you see over here. So I would probably do it as 0.15 times 12 times P plus 4% 12 times P times this guy minus the thing that you see over here. Yeah, so that gives me the 216.8 times P. So now I'm going to leave it as such. So I'm going to use that in a later step to solve for the unknown P. But first, I need to know what is now the variance of this random, of this future loss random variable. And in order to get the variance of this thing, I will rewrite my present value random variable over here. I will rewrite that using the endowment identity that we used earlier on today. And this is the connection between a life annuity, the EPV of a life annuity, and the EPV of a life insurance product. And of course, here I'm using the random variables underlying these products. Yeah, so this is a connection that we developed earlier on. And that helps me here, because if I replace the EPV, or if I replace the present value random variable with this thing, then I can more easily work with the variance of this v to the power k something. Yeah? So I plug that in, I put the terms together, and I recognize that in the expression for L, the only random variable that kicks in is over here. And that's this v to the power, and then the current future lifetime expressed in months plus 1/12. Okay, so if I want to calculate the variance of this future loss random variable, then I'll be working with this constant squared times the variance of this random variable. This is another constant, but that will drop if I calculate the variance of this L. Yeah? So we wrote down the loss at the level of an individual policy. We calculated the expected value of this loss, and we calculated its variance. Yeah, and for the variance, you have to be a little bit careful. So here I'm using this trick so that in the end, I can express the variance of L in terms of the variance of the random variable that you see over here, and which we've been using earlier on in the course. So if I actually do this, I'll get the following variance for the random loss variable, the L0I of an individual contract. So I get my constant squared, and here you recognize the variance of the present value random variable of a whole life insurance that pays at the end of the month. And why do I end up with this term over here? That's because here, if I look at the v to the power, the current future lifetime expressed in months plus 1/12, then I'm actually looking at the present value random variable of a life insurance that pays at the end of the month of death, right? So we learned in chapter 4 how to calculate this variance. So putting it all together, I've got an expression for the variance, and thus also for the standard deviation, that is a function of the unknown premium P. So I've got an expression for the loss as the expected value of the loss as a function of P, and I've got an expression for the standard deviation of the loss random variable as a function of the unknown P. So putting that together, I'm going to solve for the unknown P that matches my condition. And in that set, or in that last step, I'm going to use my number of policies, the 10,000, And I'm going to say, yeah, what is now the total loss? That's the sum of all the individual loss random variables. So the expected value of L is 10,000 times the expected value of the individual loss random variable. And the variance can be expressed like this. So that's 10,000 times the variance of an individual loss, of the individual loss random variable. Yeah. So both are functions of the unknown P. We're going to use the central limit theorem. And we're going to say the probability that the loss is negative can be evaluated as the CDF of a standard normal evaluated in this expression. We plug in our expression for the expected loss on the 10,000 contracts. We plug in the standard deviation of the loss for the 10,000 contracts, and we put that equal to the requested probability. In this case, a probability of 95% to make a profit. And of course, from your knowledge of the distribution of a standard normal, you then know that the expression over here between the brackets should be equal to 1.645. And then you can solve this for the unknown P, and that will give you the so-called portfolio percentile premium. So that's how this principle goes. So we did a couple of steps. We started with a single contract. The loss for a single contract, its expected value, its variance. Then we stepped to 10,000 contracts. We used the central limit theorem, and we said, okay, that gives us a condition where we match a function of the unknown P to a particular quantile from the standard normal distribution. We solve for the P, and that gives us the so-called portfolio percentile premium, right? A thought that I could add is, yeah, what happens if I have a general N, so a general number of contracts instead of 10,000 contracts? Well, what you see here is this 100 here. That was in fact coming from N divided by square root N in the expressions in the steps that we took, right? So what you get here is a square root N, that's the 100 here, a square root N that appears in this expression. So if you let the N run to infinity, then you can bring this square root N to the other side. If you let the N run to infinity, then you're going to look for the premium P such that this expression becomes 0, right? Because if I bring the square root N to the other side, I'll get an expression here that runs to 0, and I'm getting a premium that is the actuarial equivalence premium once again, because then I need to find the P such that there is an equivalence between the EPV of the premiums and the EPV of the benefits. And that's what's coming up over here, because that was essentially coming from my expected loss. So in this case, if the N goes to infinity, I'll need to come up with a premium such that the expected loss on a single contract is 0. So then you retrieve the equivalence premium as a limiting relation for this portfolio percentile premium. As a final additional thought, so what is happening then, in fact? So we say, but this is more in detailed studies in chapter 11 of our book. We say that the insurer in the last setting, that the insurance company diversifies the mortality risk, and a diversifiable risk. The condition for that is that the standard deviation of the total loss divided by the number of contracts, that would run to 0, that becomes predictable. Okay, and that's what you see here happening, but this is discussed in more detail in chapter 11 of the book, which we will not cover in this course.